Hello, I'm Julien. I'm the project manager and lead developer of RocSlope2. Today we're going to talk about modeling water pressure in RocSlope2. RocSlope2 is our latest program, which performs 3D limit equilibrium analysis of rock slope susceptible to wedge, planar, and toppling failures. This is of interest to engineers who might be designing, for example, dam abutments, where water pressure plays a role in the factor of safety of their slopes. And we're going to look at how we can model water pressure acting on slope faces and even joint face in RocSlope2. Let's take a look. Here, we're looking at the design of a dam abutment in RocSlope2. So let us quickly take a look at the geometry of our dam. Going into the geometry dialog, we can see that the slope face of our dam dips at an angle of 70 degrees and has a dip direction of 45 degrees. We can also see that we're modeling our dam to have a height of about 20 meters and a spanning length of 50 meters. Also modeling an upper face at a slight inclination of 5 degrees and having the same dip direction as the slope face. And finally, we're setting the dip of our overall base inclination, which is used to generate our toppling blocks, to 42 degrees. In RocSlope2, water forces can be applied to two types of faces. These two faces being our slope faces, consisting of our slope and upper slope face. And the second type of face which water pressure can act on is our discontinuity or our joint face. To model water pressure acting on our slope face, we need to define a ponded water pressure. We can do so by going into slope properties, then going to the water parameters tab and enabling ponded water by clicking on apply ponded water. The program will prompt us with two additional parameters, being the ponded water elevation and the ponded water unit weight. The ponded water unit weight is defaulted to the unit weight of water, but the user is not limited to this unit weight and is free to change it if they wanted to model some form of slurry or tailing materials. And the ponded water elevation will have an impact on whether the water pressure is acting on the slope or upper slope face based on whether these surfaces are submerged. For this example, we will assume that the ponded water elevation is at 0 meters, which coincides with the slope crest, and that the ponded water unit weight is the same as the water unit weight. Clicking OK will add water surface to our model as shown here. And we can also see that the factor of safety for all of our analysis has changed and indeed increased. This makes sense because the water force is actually keeping the wedge block and planar blocks in position and preventing them from sliding. In the case of the toppling analysis, the water force is reducing the driving force causing the blocks to topple. We can also look at the pressure values at different locations along our slope. This can be done by going to the Results tab. By clicking on Show Water Contours, users will see the water pressure on each block for each analysis. For example, looking at our wedge analysis, we see that there are 3 blocks being formed, and we can investigate the water pressure effects on each of these blocks by simply double-clicking on the row of interest in our results grid. And here we can see that for this block, for instance, the maximum pressure acting on the slope face is around 70 kilopascal. And in the case of the first block, the maximum water pressure is around 195 kilopascal. This is again in line with the results which are being shown, with the block having the highest water pressure acting on it having the highest factor of safety. Looking at our planar block, we see that the factor of safety has increased again, but we have a single block forming. And finally, looking at the toppling block, we also notice that the factor of safety has increased, again in line with what we would expect given the direction of the water force. Note, however, if I rotate my slope and take a look at my joint surface, that there are no water pressure contours shown on either surfaces. The reason being that ponded water pressure is assumed to not penetrate the slope face and is also assumed to only act on the slope face, whether it being the slope or upper slope. In order to model water infiltration and see the impact of water pressure on the joints, we need to define a groundwater method. Let us define a groundwater method and see how is water infiltration impacting our dam abutment model. In order to model groundwater in our joints, we go to joint properties. We go to the water parameters tab of each joint we want to account for water pressure and click on the apply groundwater checkbox. Here we see that by default, all of our joint properties have the apply groundwater checkbox already selected, but we still don't see any water pressure acting on any of the surfaces shown in our model. This is because if we go back to the slope properties under water parameters where we've defined our ponded water pressure, we'll see that the groundwater method is defaulted to dry. We have 3 different ways of defining a groundwater in RocSlope2, starting with elevation. Similar to how we've defined our ponded water pressure, we can define an elevation for the water surface which impacts the water forces acting on the joints. We can choose the water surface. The user has the ability to draw a phreatic surface at the location of the water surface for any of the analysis and any of the blocks being analyzed. And finally, the user can specify water pressure by choosing custom pressure. In this case, it's a constant uniform pressure, which is acting on the submerged portion of the joint surface. And the user can enter a value of pressure which they would want to model on their joint surfaces. For this example, let us choose water surface. Choosing water surface will prompt you with 2 additional parameters. Again, the user can choose to change the unit weight of the liquid under investigation if they were dealing with some sort of other liquid materials which infiltrated their rock slope and had an impact on the factor of safety. And you also have a value of HU, which is a factor applied to the water pressure being computed. We'll leave the default values for this example. And we will now draw our water surface. We simply have to enter into the 2D view of any of our analysis mode. Let us start by going into the individual view of our wedge analysis and click on 2D view as shown here. Clicking on 2D view will bring forth a 2D view of our slope on the right side of our model. And you will notice that in the ribbon, the phreatic surface is now enabled. To add my water surface, I simply click on Add under phreatic surface. This will change my cursor into a crosshair and enable me to draw a polyline defining water surface. For this case, my water surface is located slightly below the crest of the slope and goes in a straight line as such. Now that I've drawn my phreatic surface, I can click OK. And again, we automatically see the effect of this new component in our analysis on the factor of safety. The water surface which was added to wedge analysis or the wedge block will also propagate to all the other analysis. So the user doesn't have to define a water surface for each analysis again, all over again. And we can see that in the case of the planar and the toppling analysis, the factor of safety has drastically decreased and has reached a value of less than 1. Now, again, we want to see the water pressure contours, and rotating my block as such, we can now finally see a water contour applied to our joint. Here, we see that the maximum pressure is occurring at the tip of both my toppling block and my planar block. And in the case of the wedge analysis, the peak pressure is occurring at the toe of my wedge block, with the highest pressure acting on the first block, as shown here. Having this information, the engineer can now mitigate the effects of water pressure by either adding a support system or changing some of the geometrical parameters of the slope, such as the slope face angle. And the aim would be to have all of the analysis and all of the blocks have a factor of safety, again, above the design factor of safety. This brings us to the conclusion of this demonstration. Thank you for watching. If you have any questions, please leave a question in the comment section and see you in the next video.